In example 5, we're going to return to a function that we introduced a while ago, the square root function. And when we write z to the 1/2, what we mean is we mean the principal square root. And what does that mean? Well, if we write, if we think about the argument, right? There was two choices for our square root. We could take either the principal argument or the principal argument plus pi, plus 2 pi, and then divide that by 2. So in this case, what we're going to be doing for the principal square root is we're going to build off of the principal argument. So we're going to take the square root of the modulus of z. That's like the normal real numbers. But then the complex part is adding in some argument component. And it's going to be using the principal argument. So which argument do you take for the principal square root? You take the principal argument. So in this example, all we're going to do is we're going to compute some values. So a, if we have z equals 4, we want to know what 4 to the 1/2 is, meaning the principal square root of 4. Okay, so what is it? Well, it should be, well, what do we need to do to compute this? We need to compute the modulus of 4. The modulus of 4 is 4, great. And we need to compute the argument, the principal argument of 4. The principal argument of 4 is 0 because it points on the positive real axis. This tells us 4 to the 1/2 is the square root of 4, e to the I times 0 over 2. In this real part, this also uses the principal square root for real numbers, right? Because there's two square roots of a real number, usually, if the real number is non-negative. And so this one will spit out the positive, where it could also spit out the negative. And then this is e to the 0. That's just a 1. So we get 2, like usual. And then the other one, the non-principal one, is of course just negate that. If you have one square root, you negate it to get the other square root. Great. Let's try a purely complex number now. Let's look at negative 2i. And again, here, negative 2i to the 1/2 is the principal square root of negative 2i. And so we need to compute its modulus. The modulus is 2. And we need to compute the principal argument of negative 2i. Negative 2i points directly down negative 2. So it's negative pi over 2. So it's not 3 pi halves, it's negative pi over 2 for the principal argument. And that will affect your answer. So make sure, if you need to review that. So this tells us then that negative 2i to the 1/2 is going to be square root the modulus, and then e to the I times negative pi halves over 2. So that's the square root of 2, e to the negative I pi over 4, which we can do some more math on that if we wanted to. And that's root 2 cosine negative pi over 4 plus I sine negative pi over 4. And that's going to be root 2 positive root 2 over 2 rather, plus I times negative root 2 over 2. And we multiply through by root 2, so it's going to make our coefficients 1. So we get 1 minus I. Let's just do a quick check. 1 minus I squared is 1 squared minus 2I plus negative I squared. So that's 1 squared minus 2I minus, well, that's 1 minus 2I minus 1. It's negative 2I as desired. Great. So we found a square root, and this is the principal square root. And let me just point out here, the non-principal one is just negate that. Okay, so if we were to graph the principal square roots, so here's negative 2i down here. The principal one is 1 minus I, so 1 minus I. Here's our principal one. And then the other one is negative 1 plus I. It is a square root, but it's the non-principal one. Great. So we've done that computation. Let's do one more for this example. Let's look now at z is negative 1 plus I. So again, we want to compute, this is number c, we want to compute the modulus of z, it's the square root of 2, and we want to compute the argument of our z, and that is going to be, let's see, negative 1 and up, so that's going to be 3 pi over 4. So then, our negative 1 plus I to the 1/2, the principal square root, is the square root of the square root of 2. And that's e to the I times 3 pi over 4 over 2. So that's 2 to the 1/4 power, e to the I 3 pi over 8. And you can compute cosine and sine of 3 pi over 8 using combinations of trig formulas. I'm not going to. So as far as we care, this is a perfectly acceptable answer here. We could even draw it if we wanted to. So here's negative 1 plus I. Here's our z. And we have to go 3 pi over 8. So if we were to chop up the first quadrant into 4 pieces, we need to go 3 of those pieces. And we need to go out about 2 to the 1/4. So it's not quite out to, it's sort of a little bit past the circle of radius 1. So it's about here, I would say. Right, so we square that, we're going to get it pushed out just a little bit further. If we square the modulus, it'll get pushed out a little bit further. And then, of course, the angle is going to double, so it's going to go over to the right spot. So this is the principal square root. And then the non-principal square root is on the opposite side of, well, it's in the third quadrant. We negate that. I'm not going to draw it, but you can. We're noticing something here for the principal square root, at least. In all cases, well, at least in the cases we considered, if we were to imagine that the real axis as like a barrier or as a divider, then the principal square root is the square root on the same side of the real axis. Now that's not strictly true, of course. If you're on the real axis, it doesn't really make sense what I said. Most points are not on the real axis. And so for points that are purely negative, we know that the square root involves putting an I on the regular square root, on the square root of the positive version. And when you're positive, you just square root yourself like a real number, so you stay on the real axis. So it's not strictly true, like it doesn't make sense if you're on the real axis, but it does make sense if you're above or below the real axis, right? Because if you're above the real axis, your argument's going to be between 0 and pi. When you half that, it's going to stay between 0 and pi. And when you're below the real axis, your argument stays between negative pi and 0. And when you half that, it's also between negative pi and 0. So, anyways, we can think about the real axis as a divider for computing our principal square roots. And that's 3 examples of computing them.